what we are going to do is, this is the pipeline when we do any type of ice measurement. The idea is to have an excitation system, signal, or whatever that goes to a fuel cell system or an electrolyzer. Then we measure the signals that are there. And so the idea is, so we measure the signals here. Why we are doing this? We are doing this because we would like to have access to time domain data. This is quite important, as you will see. On this time domain data, then we do ice measurements. We do it either by using sine signals, as you typically do, or you use multi-sign signal in order to speed up time. What we are doing is we are using a particular stochastic excitation called discrete random binary signal. And I will dedicate the complete second day tomorrow to describe the inner working of how we are doing it. So today I'm going to show you the overview, but I really would like to spill out the guts of how we are doing it. So tomorrow we're going to go in huge details. And because we do stochastic excitation, we can treat ice measurements as random functions. And by doing so, we are able to use some sort of a statistical analysis in order to track changes in the impedance curves without looking at them. So automatic change detection becomes very, very easy. Today, what are we going to focus on is what kind of excitations we are using and how to validate the results that we are getting. So let's go. What are we going to go over today? I'm going to give you the basics of system identification. We are going to move from mechanical to electrochemical systems. I'm going to describe what Kramer-Kronig relations are, where do fractional order systems come from, and basics of distribution of relaxation times. So, first of all, I'm maybe jumping a little bit abstract. I am an electrical engineer, and ice belongs to a particular field in electrical engineering called system identification. So that is a field that focuses on characterizing any kind of system, regardless of the nature. Electrochemical system is just one type of them. So for that field, ice is just another application of the same theory. So what I'm going to show you now is I'm going to use a lot of terminology that comes from the system theory, but I'm going to translate them to what we are used to as a jargon in electrochemistry. First and most important thing to know is that we are capable of handling linear, stable, and causal systems. So this is a mouthful. Let's describe each of these words. So linear system means that the output is a linear combination of the input, which means that if this is the same system as this one, it doesn't matter where the multiplication is. I can multiply the output, or I can multiply the input. These two things will be identical. If the system was not linear, let's say it was doing square, it would be really different if I do axt square or I do epsilon times a. Ice is applicable only to linear systems. The next thing in this title are stable systems. So a stable system is a system that returns to a resting point after some excitation. So imagine if I have a bowl like this here, and I flick this marble on some side, it will, I don't know why it's okay, it will oscillate and then it will settle down here. But if I have the ball upside down and if I flick the marble, it will just fall off and go to infinity. So we are focused on stable systems. One would say that unstable systems should not exist. They will anyway destroy themselves. Well, actually, we are building unstable systems on purpose. Fighter jets are typical unstable systems because unstable systems can be easily maneuverable. A human person cannot fly them. We need a computer to stabilize them. But when we want to maneuver them fast, we can just exploit the fact that they're unstable and move them around. So actually, we are building unstable system on purpose, but what we are going to focus is on the nicer part, stable system. And final word in this thing is causal system. And this is something that you don't have to worry about. It says that the system output depends only on the history. So the system cannot look in the future. No one can look in the future. But as with the previous case, we can build a non-causal system. A typical case is a CD player. Most of you are so young, you've never actually used it. It's a CD, you know what it is, with audio signal on it. And because it has adaptive filtering, the laser actually reads the music that will come in the future, so it can adapt. So this is a non-causal system, but all real systems that we see are always causal. So everything that I'm going to talk now is going to be applicable only to linear, stable, and causal systems. So first thing that we have to introduce is something that is called a transfer function. This is where impedance comes to. So let's forget for the time being of our complex system and let's focus on a simple mass damped system. So we have a fixed area, we have a weight, and we have a spring and a damper. And our input signal will be a force applied here, and the output will be the position how this mass oscillates. This is a very simple case. We can easily write the differential equation that describes this motion, and we can solve it. But not every differential equation, I mean, solving even this differential equation requires some integration. It is difficult for us. We don't want to do it. And that's why we have something called Laplace transform that is applicable for linear differential equations and changes their solution to simple algebraic manipulation. So before dwelling, if you don't know what Laplace transform is, this YouTube link is a 20-minute video that you can look at it, that you can get a really, really fine overview of what Laplace transform is. I'm going to try to do it in a nutshell in 2 or 3 slides. So we know what a Fourier transform is. It finds a frequency in a signal. So if we have a sinusoidal, it will just print out which frequency is it. Laplace transform does 2 things. It finds which sinusoidal is present, and in the same time says whether it's exponentially damped, it has fixed amplitude, or exponentially growing. So it gives us the exponential part and the frequency part together. Why is this important? Well, on the left-hand side, you can see a sine signal, and you can see a Fourier transform, and if we calculate this, we'll have a peak where this 2x is located. On the right-hand side, we have 2 relations. The top one is the Fourier transform, and the bottom one is the Laplace transform. On the first glance, the integrals are identical. The only change is here we have integration to 0, because as engineers, we think that the system at time 0 starts. Before that, it was nothing happened, so it was 0. And the other change is that instead of j omega, we have s. So this is not just a simple change of notation. It is much more profound. This s is actually this part. So it is the original signal multiplied by exponential decay. And that is why with the Laplace transform, we can get the frequency that is happening plus the exponential decay or exponential growth. If alpha is 0, then we have a Fourier transform because we will just have a sign that is multiplied to the e to the power of 0, which is 1. Why is this important for us? Because now, if I go back to the differential equation, we can, there are a set of, we don't have to use these integrals to solve this differential equation. The tables as we have for Fourier transform, we have the same tables for Laplace transform. So if we have second order derivation, we multiply it by s squared. First order derivation, we multiply it by s. So there are simple rules, and we transform this differential equation to something like this. And then by algebraically rearranging, we are getting this relation. So it's input, so it's output versus input. And this here, it's called a transfer function. And this is the impedance that we are looking at. Why is this important? The transfer function doesn't always have 1 in the numerator. It can have some parts, but we can ignore them for now. The important part is in the denominator. Why? Because in our case here is a square equation, which means that it has 2 solutions where the denominator is 0. And when the denominator is 0, this g of x function becomes undefined. It's something divided with 0. And these points where this denominator is 0 are called poles. And these are the most important parts that define how the system behaves. Why? So in this case, the poles can be complex because it's a second order equation. So on the imaginary axis, we are getting the information about the frequency. On the real axis, we have about the damping over time. So if the pole is here, we have some frequency, which is here, and we have negative damping, e to the minus a, which means that that frequency will decay over time. If we go on the other side, we have a different frequency, a little lower than this one, but we have a positive exponential. So this will grow over time. If we have a pole here, this means that we will just have oscillation because we're multiplied to e to the power of 0. And these poles are actually defining the resonant frequencies in our system. These are, if you ever done distribution of relaxation times, these frequencies correspond to the peaks in the DRT. So our goal, ultimate goal, is to find where our transfer function has these poles. This is everything that we need to know to characterize the system. So this is easier said than done. How can we do it? So typical way to do it is, because this is a frequency domain, real and imaginary, over omega, we can write its amplitude, g over s, versus frequency, and its angle, g of s over frequency. So this means that I can take, so wait, let me go back. So let's assume I made a simple demo just to give you an idea, mechanical system. We have 2 weights. Imagine a car. A car is the yellow one, and the wheel is the blue one. And when the wheel hits a bump, we can see that the car will oscillate together with the wheel. And let's characterize this system. So we are applying a sine signal on the blue weight, and the yellow weight oscillates also. We take the amplitude of the input and the output, we divide it. Then we take the phase difference between those signals, and then we have amplitude and phase, and we draw a single point in our frequency characteristics. Change the frequency. Now the output is a little different. Again, the same idea. Take the input, take the output, take the phase difference, and we calculate all of this. We have another point. And as the frequency increases, you will see that the yellow weight will stop oscillating that much. Its amplitude becomes smaller and smaller. It means that the system doesn't react to such high frequencies. This will be now the last scenario, when we apply a really high frequency input. So we have another point. It's not clearly visible. So if we have a really high frequency, the output doesn't react. Simply, it doesn't have a bandwidth. We repeat this thing, but the ratio is now really small. Yes, phase. And then if we do it over a very, very large set of frequencies, we are going to get something like this. And this is what we are doing when we are doing ice. We are not throwing our fuel cell up and down, but we are exciting it with electrical signals. But this is the same concept. So what is different than what we have here? First thing is that the model is unknown. And in this case, I already presented you what the model was, but we don't know the model. The only thing what we can get is the frequency characteristic. This is now just the amplitude. I should have drawn the Nyquist curve, but this approach is applicable only on linear, stable, and causal systems. That is the one thing that should keep in mind. There are also publications that do a form of so-called nonlinear ice and stuff like that. Yes, you can calculate this, but the analysis of the results can be a little bit tricky. And finally, why we are doing this? Because changes in the frequency characteristic indicate changes in the system. So first things first, we have to find whether our system is linear. It's not. Mother Nature doesn't provide linear systems. Very, very rarely. There is this joke like there are two types of differential equations, solvable and useful. Everything that is useful is most probably not solvable. So what we do is we do an IV curve and we try to find a place where, a set point, where we can say that our system is sufficiently linear or as close to linear as possible. So those are called pseudo-linear. And at that point, we have to find how big amplitude we can apply. Because if we apply here really big amplitude, we won't be able to assume that the system was straight, because this is applicable only in this small interval. So this is something what we have to do. So now, how are we doing these things in electrochemical setting? So instead of using mechanical signals, we use electrical signals. We use current and voltage, depending whether we do galvanostatic or potentiostatic excitation, but it doesn't matter on the case. So we have input signal. We calculate the ratio of the amplitude of the input versus the output, plus the phase difference, and we start doing this over and over again. Why is it important to know where we are doing ice? For example, case A, we are doing it in a linear region and everything holds. But in case B, we excite with this signal, but because we are near this knee part and the amplitude is quite big, the output is not really a sine wave. It's distorted sine wave. And the result that we're going to get here, we can calculate the ice, no problem, but the result that we're going to get will be questionable. So what do we get at the end? Because everything that I draw up to now was an amplitude and phase, what we are actually doing is we can take this and write it like amplitude e to the j omega phi, and we can plot real and imaginary part and get the Nyquist plot. And this is what we are doing all the time. So when we had a mechanical system, we have these dampers, springs, and stuff like that. In electrical settings, we use resistors, capacitors, and inductors. I'm pretty sure that you are all aware of this. There is one peculiar stuff about electrochemistry. There is a concept called fractional order differentiation. It's not present only in electrochemistry. We can have a mechanical system that is fractional order. It is, we are used to having like a sliding surface where we put objects and they slide. But if we take a curve that is called tau-tacron curve, it's not a parabola, it's a little peculiar curve. It doesn't matter where you put these small balls, they will, regardless of the starting point, they will reach the end in the same time. And if we try to solve the equation of motions of this kind of system, a fractional differentiation of order 0.5 pops up. This was first noticed by Abel, and he wrote a letter, not an email, a letter to Liouville saying that, look, I come up with this peculiar concept on which the answer was, this is a rather strange mathematical concept, but I'm pretty sure that someone in the future will find a use for it. And here we are. So why is this important? Well, instead of having capacitors, we now have constant phase elements. We have Warburg elements, and we can do vast majority of these components. So what is our ultimate goal in this case? We have, this is a PEM fuel cell, obviously, but it doesn't matter. We have on the upper left part of the slide, we have a system that we would like to characterize. So we calculate the ice curve and get the Nyquist curve below here. And then we actually have to, what we usually do is we put some sort of equivalent circuit model. So we take building blocks of what I described previously and try to mimic the measured Nyquist curve with some model. The problem with this is that we are not always sure which model to use. Fractional order identification is rather problematic, which I'm going to provide a little bit more details. But this is current state of affairs of what we have in the field of ice. So what is our goal here? Depending on the electrochemical system at hand, the impedance characteristics can be vastly different. On the left-hand side, you have a battery. On the right-hand side, you have some sort of fuel cell. Doesn't matter which one. We can clearly see that both of them have clearly different ice configurations. So, what is our goal here? We want to do system identification. We want to identify our fuel cell. And we have three main scenarios how we can do it. We can do a white box where we know the transfer function, which most probably it is very rare case. We have a black box, we don't know nothing, and we would like to identify it. and a gray box where we can be somewhere in the middle. The first thing, what we are taught in school when we do system identification is we should not overestimate our own knowledge. We should not go and say this system has this structure. We know the transfer, we know the impedance model, we just need the parameters. There might be issues that model might be wrong, our assumption, or maybe the signal to noise ratio is not good enough, maybe the frequency is not good enough, so we will not be able to identify everything. And the very, very important part at the end, for linear, stable, and causal system, it is completely equivalent whether you do identification in the frequency domain, that is, you try to use ice curves, or you do the same identification using time signals. So either whether you do in frequency domain or in time domain, the results are equivalent. And I'm going to show you now that we do some of the parts in the time domain because it's a little bit more time efficient. Okay. So how do we do ice? The naively way, no one does it, by the way, like this. But this is the most clear way for you to understand how we do it. So exactly the same as my example with the weight. We excite it with, let's say, voltage, and we measure the current. We calculate Fourier of the voltage, Fourier of the current, take the ratio, and we get the ice curves. And we do this for each and every point, and we get these small dots here. And we calculate the ice curve, and this is what we get. So I have to say, this is quite explainable. No one does it like this. Even if you buy Zanner equipment or biologic that does only sine waves, I'm going to show you tomorrow how they do it properly because of noise issues. But this is, if we have a noiseless scenario, this works, and this is quite nice. So the one thing that we have to get in mind is the duration of the excitation is important. Why? Sorry. As you see here, we have a Fourier transform. If you remember from the slide before, the Fourier transform had integration from plus to minus infinity. Well, if we have a short signal, let's say only one period, and this is a 10 Hertz signal here, this signal is not infinitely long. And if we calculate Fourier transform, we will get this plot here. There is a peak around 10 Hertz, but what we are looking at, it's called spectral leakage. As we increase the number of periods, 5, 10, 100, this spectral leakage reduces and our measurement becomes more and more precise. Take care that the y-axis is logarithmical, just to emphasize, to make this effect much more visible. So one might say, okay, fine, we're going to use 100 periods and we're done. For high frequency identification, this is okay. But if you go low frequency, for example, if you take 0.1 Hertz, this is 10 seconds long times 100, this is 1,000 seconds long measurement time only for one dot. So in some cases, this is acceptable. In some cases, it is not. Next case scenario is, let's put multiple sine waves, sine signals within a single one. It has a rather peculiar spectrum, doesn't matter, but we can do it multiple points at the same time. Yes, you can do this. But in the same line of thought, why not use all points at the same time? Can we do it? Actually, we can do it. There is something called white noise. And why is this important? So this part here is the derivation that we have previously. So this y was the output and u was the input of the signal. And the question is, if we put u of s as a constant 1, then what we are going to get is G of S equals U of S over 1. So the output of the system will be our impedance. Only one signal. So all we have to do is we have to find a signal that has a Laplace transform constant to 1. And we know it's called white noise. Or actually, in this case, it's a Dirac signal. It requires infinitely high amplitude. It's really hard to do it. But what we can do actually is we can generate a noise-like signal that has a flat spectrum. And what we have is we have a flat spectrum here multiplied, but whatever characteristic we have here, so we multiply this by 1, the result will be the characteristics that we are looking at. So all we have to do is not use sine waves, but use a signal that has such spectral components. So all frequencies are present at all the time simultaneously. So how we do it? This has actually two benefits. First, when we do an excitation with sine waves, we need sine waves to be crisp. There should not be any nonlinearities in the sine waves, because if there are nonlinearities in the sine waves, they will mirror on the output. And that requires quite a complex hardware components. We can generate such a broadband excitation signal by following something that is called a telegraph signal. I'm sure you know of Morse code, this beep, 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 beep. So it is like a signal that can be on and off, on and off. And how we can generate it? There are only one thing that we need at this point. What is this highest frequency that we are going to look at? And we can decide this because we know that, for example, our fuel cell above 10,000 hertz is the ice curve just stops. So the ice curve may be like this. And here is 10 kilohertz. So we can say that, okay, we can go up to 10 kilohertz and we will capture everything what we have in our fuel cell. So all you have to do is, based on this wish, you define this parameter lambda. And how you generate the signal? Every lambda seconds, you throw a coin and you say, if I have a tail, I switch the signal. If I have head, I keep it as it was. And I do it constantly. Lambda seconds, flip, change. Lambda seconds is the same, lambda seconds the same. And you switch it like that, and this signal has such a structure. Generating this signal is really easy. From a hardware perspective, it's just one switch, a FET transistor. It is really cheap. You can do it off the shelf. It's really, really efficient. But now the fun part starts. All the frequencies are present. I told you that all the frequencies are present all the time. Well, that wasn't true. All the frequencies are present on average all the time. This means that, This means that if I take this signal and I calculate it using time frequency analysis, I'm going to tell you tomorrow really, really in detail what this means. So it's as if we calculate Fourier transform for a window and draw it here and another window and so on and so on. What we can see is that, for example, this frequency occurs here, but it's not present here. Then occurs here, but not present here. But if I do average over time, all of these frequencies have on average same power. This doesn't mean that they're always present. It means that they're present on average. Now this might be a rather strange concept. So this means that a sine signal is present, then it's off, then come on again, then off. Yes. So how do we calculate impedance out of this? So it's actually rather simple, and for that purpose, rather numerically efficient. So what we do is, we take this excitation, and whether we are doing it in galvanostatic or potentiostatic mode, it doesn't matter. We do it either on the current or on the voltage. We measure the output. We do this so-called time frequency analysis. I'm going to describe this pipeline in day 2 completely. This pipeline will be day 2. We calculate this chaotic picture, and then with a huge quotation marks, we divide it. And then we get ice over all frequency ranges at one click. So we have simple excitation, cheap hardware, computationally efficient algorithm, and we obtain everything in a single point. To be even more flamboyant, we are not even limited to number of points of decade. We can decide how many points we can do. When we calculate ice with this approach, we usually use something like 80 or 100 points per decade. So over 3 decades, our ice curves have 300 points or more without compromising the measuring time. So let's recap what we have up until now. So we have a system that is linear, stable, and causal. We can excite it using sine signals. We know how to do it. We can excite it with composite signals. We know how to do it. We can excite it with almost white noise. I just give you a sneak preview. Tomorrow I'm going to show you how you can do it. And we can obtain ice curves. I draw here 3 ice curves. All 3 of them must be identical. It is regardless how you excite the system, because the system is linear, stable, and causal. Regardless of the way how you do it, the results must be identical. That's the fun part about it. So we know that our system is stable. We know that it is causal. The fuel cell cannot look at in the future. The only question is, did we do it properly? Are we in a linear stage? So the next thing, what I'm going to present today, is something called validation of our ice curves. Are the ice curves correct? Not by looking at it, are they mathematically correct? So what are the conditions? Where the second column of this table will become clear tomorrow, but for a single or multi-sign components, we usually do non-commensurate frequency. So that means we have frequencies that are not linear combinations of the others. We can do simple impedance calculation using Fourier transform, and we have to check whether it's a linear region. If it's not a linear region, we can do something called total harmonic distortion analysis. For stochastic signals, this becomes a little bit more complicated. On average, the amplitude of each component must be 0. Why is that? Because if it's not 0, this means that over a long time, there will be a huge energy output, and we don't want to use that much energy. So we have to keep the energy almost 0. And second thing is, no 2 spectral components can be correlated. This means that if they're correlated, this means that one excitation will excite its own frequency and something else, which is, then we won't be able to distinguish whether the output is because of the excitation or because of the correlation. So the first column is rather simple. The second column, particularly this first cell, is what? I mean, mathematically, yes, we understand it, yes. How can you test this? I mean, why is this? It's rather abstract, but actually you can test it really simple. It is something what is called Kramer-Kronig relations. So don't be alarmed. This is the first time when I'm going to show you that On my slides, there will be a lot of these huge sausagey integrals with a lot of Greek letters that will boil down to simple Python one-line codes. So the implementation is extremely simple, although mathematically it might seem rather appalling. So what these Kramer-Kronig relations say? Let me draw a Nyquist curve and say it by definition, and then I'm going to put it in a normal human speech. So we have here positive frequency. This is frequency 0, this is frequency infinity. And as we know from Fourier transform, there are also negative frequencies. So I'm going to draw it in different color. So this is the complete ice curve. So this is the negative part. And Kramer-Kronig relations state the following. The red curve is a complex function because it's a transfer function. We know it's complex. And it says this: a transfer function of a linear, stable, and causal system is analytical in the upper half plane. That is the definition. What does it mean? If you had complex analysis sometimes in your undergraduate studies, there are these Cauchy-Riemann conditions that define whether a function is analytical or not. Fine. Oh, yes, you know about it. Maybe you've had an exercise and you forgot about it immediately, as did I. So what does this mean? This means actually that the real and the imaginary and the real components are connected to each other. So if I know the real component of a linear, stable, and causal system, I can generate the imaginary. And if I know the imaginary, I can regenerate the real. So this means that if I measured both real and imaginary, I can check whether these two match as a pair using these integrals. And that's how I can actually check whether my measurements hold. Fine, we have a solution. But as you can see in the integrals, we integrate up to infinity. And we have this part here, x squared minus omega squared, which at one point will be 0. So these integrals are not defined. If we knew the transfer function in a closed form, we could have solved them with residuals and Cauchy theorem, and we could do it. But we have only numerical points. We have just points like this, and we have to integrate somehow. And we cannot do it. But luckily, so let's explain why is this working. This is very, very, very simple. So I'm going to talk that always that we have a transfer function g of s, which means we have some sort of impedance. And I'm going to talk about an impulse response. This is actually the inverse Laplace transform of this integral. You don't have to worry about this at the moment. We are not going to solve any integrals. Everything will be done gently. And because the system is causal, this minus infinity will become 0. So this is everything what we need at the moment. If you want, this is the next two slides is the derivation of the paper that is in the subtitle here. And the paper is called Derivation of Kramer-Kronig Relations in 2 lines. It is a half a page, 2-column paper. You should go and read it. It's really, really cleverly and clearly written. The idea is the following. We have an impulse response of a system that is causal. This means that we know that the system can exist from 0 to plus infinity in time. This is the most important part. I'm going to jump over the equations because they're not important in the moment. The trick is because the system exists from 0 to infinity, we can safely assume whatever form we want on a negative part, because anyway, we are going to multiply it by 0. So we can safely assume that either the system has transfer function like this, so it becomes an odd function, or it has function like this, it becomes an even function. And if we have this odd-even function combination, then this integral can be solved quite easily. I'm not going through details because that is not my case. You can read the paper. What this trick allows us to do is we can get fairly simple relations between the imaginary and the real components here, and imaginary and real component, and real and imaginary on here. But yet it holds this principal value integral. Still, we didn't get rid of this integration to plus to minus infinity. There is, however, one final trick up on our sleeves that is called Z-hit. So whenever you do a nice calculation with your device, biologic or Zana or whatever, this procedure kicks in. Z-hit, it's actually short for Zahner-Hilbert transform. You have the paper in the subtitle. And what these guys developed is, instead of looking at imaginary and real component, you can look at the amplitude and the phase. And the amplitude and the phase are linked with this equation. Again, there are two benefits. We are not integrating over plus minus infinity. We are integrating only over the parts that we look at. But we have this part here that is rather strange, even mathematically. But we can solve this fairly easily with something that is called, you have the access to this Savetsky-Golay filter. It doesn't matter at the moment. This sausage here is implemented with these 10 lines of code. So whenever you have impedance measurement, you can use this approach to validate whether your measurements are correct or not. This is done by impedance measurements devices by themselves. It's somewhat obscured for you, but if you do the complete pipeline, you have now the tool to validate your data. How does this look like, actually? So, because this is the first code that I provided here, I'm going to give you a demo how this works. You don't have to do anything. I'm going to demonstrate here. So this is a quite easy scenario. I'm going to restart my kernel here. So when you download everything, you just start these things. And this is the ice curve that I have. As you can see, the orange points are where I did some measurements. The blue one is just interpolation. The ice curve is flipped, so the negative goes down. And you can see that it has apparently some form of inductivity, rather strange one. There is this gap here that seems rather strange, some jumps here. So the question is this ice okay or not? We've measured it, seems plausible, and it's actually a measured device. So I start this Zahner-Hit approach, and I can plot now the original amplitude versus the amplitude that I got from the Zahner calculation. And these are the difference. They should be spot on, one on top of the other. And as you can see, I have some discrepancies here and some huge discrepancies at the high frequencies. So now I have to decide at which point should I, before doing any further analysis, I must remove parts of my ice curve that are not valid. And these are the places where the ice curve fails this Kramer-Kronig test. I can do it quite simple, saying, give me the error function. So what this does is calculates the relative error between the Zanner response and what I measured times 100. So in percentage difference. And when I plot it here, this is the relative error of my measured ice over frequencies. As we can see here, I have some wiggles within plus minus 5%, but as I go on high frequency, apparently I hit some form of nonlinearities, and here I have errors of more than 20%. So now the question is, where should I cut it? Now this is, there is no clear guideline how you should do it. What we usually do is put something like 2.5% or 5%. And when I plot it, this is the red points are the ones that should be removed before doing any further analysis. So the question is, why do we have these high frequency errors here? It turns out that our data acquisition device was not measuring simultaneously, but was measuring first, second, third channel, and so on and so on. And one can say, well, okay, that's logical. But when you do it in the high frequency, the time delay between two consecutive measurements introduces additional phase error and makes the output nonlinear. And that is why this high frequency fails. And we can see it even from the measurements. We see it here. It makes a rather peculiar arc at high frequency that is not, it doesn't feel natural. But we should remove our feelings from it. We have now a tool how to test it. So there is one thing that up until this point, I somewhat hide from you. And that was, there is this constant A lurking here. We solved this integral, but this constant A was left. So what this constant does is actually, when we are solving this integral, we have to somehow tune it to match our curve. And I've selected one value, but we can loop over multiple values just to see how this react will go. So there is a black line. This is the black line here. And these all lines are the validation based on different constants. So what you should do when you use this approach, and what actually your biologic and Zanner device does for you, it first goes over several constants, finds the one that matches the measured device closely, and does the analysis with that one. So this is what you should do as a first time, just to like make a ballpark number and then validate your ice curves. So this is the part regarding the validation. And let me show you now before we hit a break. I think that we're slowly going there, yes. So results from one of our experiments. This is a solid oxide electrolyzer done in Grenoble, France. As you can see, we were doing with different fuel utilizations. When we have fuel utilization 77.5, the ice curve, we are within a safe operating conditions. The majority of measured ice points are within 5% error. This part here, the big one, the high frequency part is the one that I told you about. It's because interlacing DAQ. It's not a problem with the measurement. But as we increase the fuel utilization, we actually move our set point towards one of the edges of the IV curve. And the system, so what we were doing is, because we have it like this, we were measuring here, and when we were changing fuel utilization, this set point slowly drifted here. Although the voltage, actually, to be more precise, this knee started to move this way. So our set point became part of the nonlinear region. And how we detected it? We detected it that it suddenly, even in the low frequency ranges, we start to look for places where our data points start to move out of the validation period. And that's how we were able, or not, this is nothing special. The instruments are doing it for you, but this is how you can detect that your ice measurements are becoming faulty. Okay, so recap, and I think that, yeah, maybe we will have a time for a question or two if we want, and then we will make a break and reconvene afterwards. So what we've done so far, I've told you that impedance equation is actually called a transfer function. We are focused in finding a time constant in this transfer function. I showed you how you can do Kramer-Kronig relations. We discussed that the electrochemical system are fractional order systems, and I gave you a first glance that you can do ice by exciting multiple frequency altogether using stochastic excitation. So in the remaining part of today, we are going to go in deep in fractional order, and we are going to glance over distribution of relaxation times. So I think that we are within time frame.